need to do is we need to compute also by hand, sorry, the correlation coefficient R. So I'll just give you a little bit of a background into what the correlation coefficient refers to. So the whole purpose of doing the covariance and then moving into the regression is to analyze the nature of the relationship between X and Y. And so what I mean by that is there some sort of relationship so that if X changes, Y will also change, or alternatively, if Y changes, will X change? And so one way that we're able to do that is by performing what we call a regression analysis. So regression analysis allows us to test whether or not certain types of relationships exist between the two variables. So let's just have a look at the variables to start off with. So I'm just going to copy these. Let's open up Excel. You'll have to pardon my incredibly slow computer. Come on. Alright, come on. It always takes forever when you don't want it to take forever. Here we go. Maybe I can pause this, sorry. I'll quickly pause this and I'll come back. Okay, so I finally loaded. So what I'm going to do is just paste in that data. Okay, and so what we're going to do now, I'll just give them the appropriate label. So this is X, this is Y. And so let's just do a quick scatter graph of this to see if there does appear to be any sort of relationship. Insert. So what are we doing here? We want to have a scatter plot, so we're just going to do the most basic scatter plot. Again, sorry about it taking so long. Okay, so this is a plot of the X and Y data against each other. And so what we have in this case, on the X-axis is the X variable, and what we have on the Y-axis is the Y variable. So we can see, even though there isn't a lot of data points, there does appear to be some sort of a relationship, a downward trend, i.e. as X increases, as we go along the X-axis, it appears that Y seems to be decreasing. Now, the nature of the relationship, in terms of what type of function is causing that, is unknown. But what we're going to test to start off with, which is the most simplistic, is just a straight line relationship. So if we were to put a straight line between these data values, or find the straight line that minimizes the error, or the line of best fit as it's quite often referred to in stats, can we then find how strong that relationship is? And we can. And the way that we do that is by using the regression coefficient. So we're going to compute that now. So jumping back into the operation itself, the formula for the correlation coefficient, or R, or the regression coefficient, or the R value is also referred to, is the covariance divided by the standard deviation of X multiplied the standard deviation of Y. So before we've already got the covariance, but we need to get the standard deviations for each of those. So we've got the respective formulas for each of them, and you'll see it sort of looks similar to what we have in terms of the covariance, except instead of having X times by Y, we've sort of got X times by X. So in this case, what we need to do, and just like before, we're going to break it apart into smaller operations. The last thing that we're going to do is take the square root. Obviously, in terms of this fraction that we have here on the denominator, it's very similar to the covariance, divided by n minus 1. The n minus 1 is because we are dealing with a sample standard deviation here, not a population. Otherwise, it would be divided by n. And so what we need to compute here as part of this sum is each of the elements, subtract away the mean, which we've already done up here, which is nice. So we've already computed that component. What we haven't done is square it. So let's do that for each of the values of X, and then we'll also do the same thing for each of the values of Y. We can then apply the sigma operator, which is the sum operator, over it to add them all up, then divide by n minus 1, and then take the square root, and then we'll have our standard deviation. So we'll do each of those components individually. So xi minus x bar squared is, we're going to take each value within this column, and we're going to square it. So this is negative 9 squared, which is equal to 81. This one is equal to negative 1 squared, which is equal to 1. The next one is 1 squared, which is equal to 1. The next one is 4 squared, which is equal to 16. And lastly, we have 5 squared, which is equal to 25. So now we've done that xi minus x bar squared for each of the x values. Now let's do the same for y. So we're going to take each value within here and we're going to square it. So that's equal to 8 squared, which is 64. The next one is equal to, where am I? 4 squared, which is equal to 16. The next one is 1 squared, which is equal to 1. The next one is negative 2 squared, which is equal to 4. And lastly, we have negative 11 squared, which is 121. Okay, so now for each of these, we have generated the xi minus x bar squared component, and then for the y minus y bar squared component, we now need to apply this sum operator for each of them. So we need to take the sum of this column and then the sum of that column. So this is going to be equal to the square root. I couldn't be bothered putting the the stuff in. So we're going to have a square root of a division, and I'll just have that as square root of a division here. Okay, so, and again, I'm sorry about all of these. So let's compute this sum. So we'll take the sum of this column here, and I'll do that again with my calculator. So that is 81 plus 1 plus 1 plus 16 plus 25. So that equals, in this case, 124. And remember, that's divided by n minus 1, which is 5 minus 1. So that's equal to, let me have a bracket there, is equal to the square root of 124 divided by 4, which is equal to the square root of, so 124 divided by 4 is equal to the square root of 31. So that becomes equal to the square, so let's take the square root of that value to find the sample standard deviation for x. So where am I? Here we go, square root of 31. So roughly 5.57 to 2 decimal places. So 5.57. Okay, so let's do the same thing for y now. So again, the first thing we need to do is take the sum of this column. So let's clear that. So that becomes 64 plus 16 plus 1 plus 4 plus 121. Okay, so that becomes the square root of 206 divided by, again, this is 5 minus 1. So that's equal to the square root of 206 divided by 4, which is equal to the square root of, so let's do 206, where am I, divided by 4 is the square root of 51.5, which becomes, so let's take that square root, so that's roughly 7.18. So 7.18, 2 decimal place accuracy. Okay, so now if we go back to the regression coefficient, or should I say the formula for the regression coefficient, aka the correlation coefficient, aka the R value, we can see that we now have the covariance, and we also have both of the sample standard deviations. So now we can find this regression coefficient. So that's equal to the covariance, which we have up here before, is negative 30.5. And then that's divided by the standard deviation of x multiplied the standard deviation of y. So that becomes 5.57 times by 7.18. So let's do that on the calculator. Whoops, sorry. So we have, where am I? Negative 30.5 divided by, now make sure you do this correctly, we need to put this in brackets. So 5.57 times by 7.18. And if you're unsure, just pause this video and have a look at what I've typed in to get the exact answer. If you're wondering why I had to put the 0 in there, that's just to make it a negative. So we're going to evaluate that, and so that becomes roughly negative 0.76, 2 decimal place accuracy. Negative 0.76. So, in terms of the mechanics, we have now calculated the covariance, and we've calculated, I'm just going to call it the regression coefficient from now on. So let's have a look to see if there's any other excuse me, any other questions that are related to this. So now it says comment on the direction and the strength of the relationship. So before we went into anything, we did talk a little bit about the nature of the relationship.